which is joint work with Panayotis Mertikopoulos, who is my colleague in Grenoble at the CNRS, and Heinrich, who is at the University of Zurich. Let me jump right into it. So what we're trying to understand and study is how in online markets there arises a fundamental trade-off. And so the idea is that we want to match heterogeneous agents that randomly arrive over time. And we can think of examples as buyers and sellers in financial markets, as clients and drivers in transportation. So we have riders who are seeking a ride, and obviously the drivers who would like to make some money on it. And more abstractly, clients and providers for markets for jobs and services. And the important thing, what we will focus on, which is highlighted in this last point, is markets for non-durables. So we will not consider retrade, but once a trade, so the clear buyers and clear sellers, and we'll think of each seller wanting to sell one product and each buyer wanting to purchase one product. And so the fundamental trade-off which we'll try to study, which arises in these online markets, on the one hand, your waiting time. So we would like to reduce the coexistence of clients and providers. And on the other hand, we have matching costs. So we suppose that different clients and different providers, and if we match them, will be differently productive and therefore have different costs of matching. And I just want to give you a very brief slide over the literature. So early on, there were search models which were trying to explain unemployment. And so here, the obvious question is, why is the coexistence of job vacancies and job seekers? And explanations were based on frictions, and more recently, Scheimer also was talking about workforce inertia, where the idea is that maybe workers who previously worked as hairdressers need some time to adapt to the fact that they might work in another occupation and might need to retrain or relocate. And more recently, in work driven by L. Ross, the idea of reducing mismatch through thickening the market came up, really focusing on how much you need to thicken a market to create better matches. And then in a recent strand of papers, this trade-off between really waiting and mismatch was studied, and I'm just listing here the most prominent ones. Quite often motivation in the paper, for example, by Akbarpour and also by Bakaran Lurcher, are kidney exchanges. So here they're thinking of one or two different types, and you're waiting until there are enough, let's say, high types or different blood types, and you're asking when should we create a matching to balance this trade-off. And in contrast to a lot of this literature, what we'll focus on is really a continuum of types where you cannot just count different blood types because they're from a continuous distribution of match costs. Okay, so let me briefly introduce to you the model. So we are thinking of a two-sided market that evolves in continuous time. And at ticks of Poisson clocks, an agent enters the market, and we will say that with probability 1/2, this agent is actually a client, and with probability 1/2, this agent is a provider. One important point here, the reason why we choose to focus on this half-half probability is that we are not modeling departures, and otherwise you would just have one market side, which is growing larger and larger compared to the other. And now we suppose that there's a match parameter, lambda ij. And this parameter steers that when a client I and a provider j is matching, the match cost wij is drawn from an exponential lambda ij distribution. So we assume that the match costs are exponential lambda ij's, and we just, the lambda ij's are arbitrary, and we assume that they're living between some bounds, lambda lower bar and lambda upper bar, and that the mean value of those lambdas is denoted by lambda. And note that here a careful definition is needed because obviously as agents arrive over time, we need to define the mean value in a meaningful way. As said earlier, each player wants to match to exactly one from the other side. And after a matching event, players who are being matched leave and unmatched players remain. So the only way to depart from the market is that you are being matched. So let me give you a brief example here, just showing how clients and providers arrive at random points in time. And a bit more notation. We denote by C of t and P of t the set of clients and providers that entered the market by time tau, and by NC of tau and NP of tau their respective cardinalities. And we will also think often about the number of agents on the short side of the market, which we'll denote by N of tau. Next, we will say that A of tau is the number of assigned or matched couples by time tau. So that's one measure long time, which we'll use to say how good a schedule is. And R of tau will, in contrast, be the number of agents in the market at time tau which remains. So those are all the arrivals minus all the departures which have been matched. Okay, so now the question is, what can a social planner do? So we are really focusing on the clearing schedules the social planner can define. And this could be, you can think of this as a market platform or a market maker. And this could be online in the real sense of the internet, but it's also the case that this is needed in offline markets such as normal auction houses. And we shall assume that information for the social planner is quite limited. He observes the agent's arrivals, but he has actually no information on their match costs. So he knows the distribution of the match costs, but he doesn't know the match costs which actually the agents have currently in the market. And so equivalently, we can think of the social planner as having to commit to clearing schedules ahead of time. The social planner has to say that he's running this market weekly, monthly, and so forth, which is actually quite often the case in many markets. And so the social planner decides on a clearing schedule, which determines at which points in time, in continuous time tau, to trigger a matching event. And this clearing schedule is now able to depend on the number of clients, the number of providers, and the number of couples which have already been matched by time tau. An assumption we make is that there is some unspecified mechanism which is able to match the two players with the lowest match cost at a given matching event. And note that actually such a mechanism exists because the impossibility by Myers and Satterthwaite relies on there being couples which are not being able to match at all. In our case, given we assume that all match costs are exponentially distributed, all matchings will be possible, and therefore there will be such a mechanism. But we'll not focus on this mechanism, but just assume that we have a mechanism which will always match the lowest cost couples. Okay, so let me run you quickly through one example clearing schedule, which is one where we match the couple when two agents are on the short side. So we have agents arriving, and now at some point there are two agents on the short side, in this case the providers, and now the cheapest couple is matched. And so this couple is removed. And then again, new agents arrive, there are two on the short side again, the cheapest agent is matched through some auction mechanism, and so forth. So let me give you the two competing objectives. The first one is the expected matching cost. So this is just for the first A couples. The cost of a given clearing schedule CS for the first A couples is given by the expectation over the sum of the match costs of all the couples in this matching. And the expectation is with respect to two things: the random arrival of agents and the match costs from the exponential distribution. Now the second objective is the waiting time. And this is just measured as the time agents are spending in the market. So we just have to integrate over RT, which is the number of agents in the market at time T. Notice here that the two objectives are measured in two different things. One, we are measuring the number of matched couples, and one, we are measuring in continuous time. we will be able, if we fix a specific utility model later on, we'll be able actually to marry those back together to measure in the same units. Okay, so let me give you a brief overview of the results. So first we need to understand what a single objective social planner would like to do. And it's quite evident that the patient clearing schedule is optimal with respect to matching cost minimization. As you just wait as much as possible and you will find the minimum cost matching. And the greedy clearing schedule is optimal with respect to waiting time minimization, because you'll just have the waiting due to the imbalance of the number of agents in the two markets. Our second result is then the following. No free lunch. There is no clearing schedule that is approximately optimal in terms of both waiting time and matching cost. Next, I'll show you the result where we consider a class of clearing schedules for multi-objective social planners who care about both dimensions, which are giving us a continuous trade-off between the two objectives of waiting time minimization and matching cost minimization. I'll briefly talk about a specific utility model for the social planner, where we'll highlight that we can actually find somewhat the optimal clearing schedule for a given utility model, trading off those two dimensions. And finally, I'll tell you about generalizing these results to non-exponential match cost. Okay, so here for the single objective social planner, without going through numbers, I just want to highlight 2 points. For the patient clearing schedule, the matching cost is actually finite, so it will not depend on the number of couples matched. Whereas for the greedy clearing schedule, the waiting time is growing with time to the power of 3/2. And this is intuitive once you note that the imbalance in the market between 2 market signs, so how many clients versus providers are there, behaves like a Brownian motion. We know the expectation of this Brownian motion is of the order of square root of time. And therefore, if you integrate over this for the greedy clearing schedule, since you will always only have the long side of the market having any agents, you will have this tau to the power of 3/2. Now comes the more exciting multi-objective social planner. And as lined out, and I think which is quite clear, is that single objective social planners are not very realistic, because one is hypothetical, waiting forever until all agents arrived, and the other one is making no use at all of the fact that there might be heterogeneous match values, and thickening the market is actually creating better matches. We'll measure the performance of those 2 dimensions in terms of 2 ratios. On the one hand, the expected matching ratio, which is given by the cost of a clearing schedule versus the cost of the patient clearing schedule, which is optimal, and the expected waiting ratio, which is given by the waiting time of a clearing schedule until time tau compared to the greedy clearing schedule. So now we are going back to our no free lunch result, which is the first important result, I think, in our article, which is saying that there exists no clearing schedule which simultaneously achieves finite ratios for both expected matching cost and waiting time. And so the multi-objective social planner is really faced with a crucial trade-off independently of the specific utility function, because there's no way how to get finite ratios for both of those objectives. And actually this theorem justifies that it will be sufficient to analyze the performance measures in terms of orders of tau, because we know that we cannot have finite approximations, so we will focus on the orders here. So now I'll give you the results about interpolating between waiting time and matching cost. And we'll recall the 2 extreme schedules. C is patient, which is optimal with respect to matching cost minimization, and C is greedy, which is optimal with respect to waiting time minimization. And we'll study clearing schedules that have a simple form that match the case couple when the number, when n minus k is equal to f of k, which means that f of k is the players on the short side of the market. And we'll choose very well-behaved functions here, and we just look at f of k behaving in the orders of k to the power of gamma, where gamma will be between 0 and 1, which is actually ensuring that all the schedules are such that the ratio of unmatched players versus matched players is tending towards 0. So we are actually matching players, not just waiting forever without matching anyone. And so here you can see the different regimes where you have the different schedules in the left-hand column. And so we have the schedule greedy on the top and the schedule patient at the bottom. And in between we've split dependent on the gamma values. And on the right two columns, we show the matching ratio and the weighting ratio. And obviously we can see that the matching ratio is increasing as we go from the patient at the bottom to the greedy at the top, whereas the weighting ratio is increasing as we go from greedy to patient, which is highlighting this trade-off. And we can see that there's this critical rate at gamma equal 1/2, where we see the matching ratio of log A and still a constant weighting ratio. And just as I said, I'll just say that if we fix a utility model where we want to balance those two ratios, we can actually find here at the bottom the balanced schedule where we have the same weighting ratio and the same matching ratio. And so this is kind of showing that we are almost able to achieve something like free lunch, but not up to a factor of log. And I just want to show you briefly the generalization, which is showing that this exponential match costs are actually quite special and really at the boundary of whether free lunch exists or not. So if we abstract away from modeling the actual edge weights and just ask ourselves, how does the matching cost decay as the number of agents in the market grows? We just say that it decays as 1/x to delta for some delta greater than 1. Then we have the following theory, that for delta between 1 and 2, there is no free lunch. And we have again a result where exactly the critical rate clearing schedule is. Whereas for delta greater than 2, there will exist free lunch. So there is a window of opportunity of clearing schedules, if you choose your gamma carefully, where you have a finite expected matching and weighting ratios. And note that for exponential match costs, we are exactly in the case delta equal to 2. So we exactly struck here with exponential match costs, the boundary where free lunch is not possible. Let me just briefly summarize. So what we study is this trade-off between weighting mismatch in the online assignment game. And we think this is quite a useful framework to think of stochastic arrival and match values. And we identify those two phase transitions.